Microwave tubes, Klystron amplifiers, second part, series on microwave engineering, lecture number 4.12. Klystron amplifiers employ an electron beam. An electron beam formed with electrons accelerated to high velocities. These electrons enter the buncher cavity gap at one instant and leaves the gap at another instant. There exists certain duration, certain time between entering and leaving the cavity gap. This duration is not the same for all the electrons. Different electrons, they have different amounts of duration for crossing the gap. Average duration is called grid gap transit time. While crossing the grid gap, some electrons face acceleration, some electrons face deceleration. Also, electrons facing acceleration. All the electrons, they do not encounter same amount of acceleration. In electrons facing deceleration, all the electrons do not encounter same deceleration because the grid gap voltage, which is input signal voltage, it is time varying, and at different instants of time, the grid gap voltage, it is different. As the electrons enter at different instants of time, naturally different electrons face different amounts, different polarities of the grid gap voltage, resulting in electrons facing different amounts of grid gap voltages. These voltages are also not constant during the time period when electron is crossing the grid gap. When the electron entered, gap voltage may be one thing, and when the electron is leaving the gap, the voltage, grid gap voltage, it will be different. But an average for this voltage can be computed. This voltage is called average grid gap voltage or average gap voltage. When electron beam passes through cavity gap, it is influenced by the voltage that exists across the grid gap. It shows the existence of interaction between cavity and beam. The amount of interaction, the amount of connection between beam and cavity, it is described by a parameter called beam coupling quotient. Symbol is B. Different electrons after crossing the grid gap enter the drift space with different velocities. This phenomena is referred to as velocity modulation. Velocity modulation is described by an analytical relation. It is called equation of velocity modulation. While traveling through the drift space, the electron beam gets converted into bunches. Bunch formation is key to the amplification mechanism that takes place in Klystron amplifiers. The amount of bunching, the bunching may be perfect, the bunching may be partial. To what extent bunching is complete? This information is provided by a parameter. It is bunching parameter. Its symbol is X. It is a critical parameter. It goes into the expressions of various other parameters indicating the performance of the tube. Bunching becomes complete or nearly complete when the distance the electrons are allowed to travel assumes certain value. This value is set as the distance between buncher cavity and catcher cavity. in the structure of two-cavity Klystron amplifiers. After bunch formation, the beam delivers signal, enhanced signal, enriched signal, energized signal to the catcher cavity. How much is the power in the signal that is delivered to the catcher cavity? It is found from the expression for output power. At one level, the functioning of two-cavity klystron can be understood easily when we notice energy is being taken from accelerating voltage source at the input end, and this energy is being injected into the signal by or via electron beam. But one can also notice the total energy taken from the source or entire energy taken from the source. It is not being injected into the signal. Only a certain fraction of the energy taken from the source is supplied, given, injected into the signal. The ratio energy or power given to the signal to energy or power taken from the source, that ratio is called electronic efficiency. These are all not only parameters that are useful in understanding or describing the physics of the device, they are also useful in specifying the performance of the device. In the present session, we focus on knowing the meaning and idea behind various parameters of two-cavity Klystron amplifiers. Now let us move to the core session. To begin with, we consider average gap voltage. The particle means the electron, while crossing, experiences varying amount of voltage. The average gap voltage during the transit of the reference electron can be found using this equation. So V1 sine omega t is the voltage across the gap. If it takes a time of tau to cross the gap, this expression 1 by tau t naught to t1, V1 sine omega t dt gives an expression for average gap voltage. It is V1 beta I sine omega t1 minus theta g by 2. V1 is amplitude of the gap voltage. T1 is the instant at which electron leaves. Theta g is average gap transit angle. Theta I is a constant. It is known as beam coupling quotient. In this diagram is shown T naught indicates entry into the gap. T1 indicates exit from the gap. From T0 to T1, the gap voltage is not constant, it is increasing. It may be decreasing also, it depends upon T0, T1 location. But here it is increasing. What is the average? The average voltage. It may be somewhere here for this case. The mathematical expression for this can be derived and can be found in terms of beam coupling quotient. Beam coupling quotient is by definition sine theta g by 2 by theta g by 2. Here theta g is average gap transit angle. Average gap transit time is there, average gap transit angle is also there. Both are related. That relation is explained here. Theta g is equal to omega tau, where tau is average gap transit time for electrons. Tau is nearly equal to d by v naught. D is grid gap, v naught is velocity to which the electrons are accelerated by the accelerating voltage, or the velocity with which electrons enter the grid gap. It is nearly equal to T1 minus T0. So tau multiplied by omega. Omega is the angular frequency of the input signal. A few points regarding beam coupling quotient. It measures the interaction, amount of interaction between electron beam and cavity gap. It can be defined as the ratio of alternating current over the cavity to the AC component of the beam current. This is a formal definition. In case of input cavity, the cavity current is due to signal input to cavity. In case of output cavity, the cavity current is due to induction by AC component of beam current. The AC beam current is due to cavity AC as in case of input cavity, or it may be due to bunches as in case of output cavity. Beam coupling quotient varies with transit angle and it assumes maximum possible value of 1 when transit angle is very small. The relation between beta, beam coupling quotient, and transit angle theta g is shown here. It is 1. Interaction between them is maximum when transit angle is 0. Transit time is small, negligibly small. So conclusion is highly accelerated electrons, small grid gaps at relatively small frequencies give a better quotient. We want the interaction more. Therefore, acceleration given to the electron beam must be large and grid gap should be as small as possible. Now, the velocity with which electrons leave the buncher gap. Note, all electrons enter the grid gap with one velocity. That velocity is indicated by V0. But different electrons leave buncher gap with different velocities. An expression for the velocities of electrons leaving buncher gap can be derived. That expression appears like this. This expression is called equation of velocity modulation. V stands for velocity. T1 stands for the instant at which electrons leave the buncher gap. Beta I is beam coupling quotient pertaining to input cavity. V1 is amplitude of the signal voltage across the gap. 2 is to V0 is accelerating voltage. Sine omega is the frequency of the input signal. T1 is already given. Theta g is gap transit angle. This equation describes the velocities of electrons when they enter into drift space or when they leave the buncher cavity gap. The quantity in the equation beta I V1 by V0. This is known as depth of velocity modulation. Another important parameter in describing the functioning of the Klystron amplifiers is bunching parameter. This fellow has certain special significance in the operation of Klystrons. It actually indicates the degree of bunching as well as the waveform of density modulated beam. There is an expression for this parameter. Its symbol is X. X is equal to beta I V1 V0. These are all already described. Theta naught is also described here as average drift space transit angle. Notice transit angle. We come across two transit angles. One transit angle refers to the transit of electron in the grid gap. This is one transit angle. Another transit angle is, it refers to transit of the electron in drift space. First electron passes through grid gap, then it passes through drift space. Electron passage through grid gap gives rise to one transit angle. Electron crossing the drift space gives rise to another transit angle. Theta naught pertains to here transit angle of drift space. It is equal to omega L by V0. V0 is the velocity with which electrons are initially accelerated to. L is the length, omega is frequency. The distance between input and output cavities is not arbitrary. It is fixed on the criteria of maximum power transfer from bunched electron beam to catcher cavity gap. For optimum power transfer, the distance between the cavities should be. This distance is indicated by L0. 3.6 by omega V0, V0, beta I, V1. Now we know the meaning of all the symbols. Omega is frequency, angular frequency. V0 is velocity to which electrons are accelerated. V0, this is accelerating voltage. Beta I is beam coupling quotient of input cavity. V1 is amplitude of grid gap signal voltage. Catcher cavity current is periodic and it can be expressed in Fourier series as. Notice initially beam is a DC current. Actually it is direct current. initially. Then velocity modulation is inflicted over it as a result of velocity modulation, density modulation, leading to formation of bunches. Then the bunches cross the catcher cavity gap one after another. It is appropriate here to recollect the fact that only half of the electrons in the beam they participate in the bunching process. Electrons that cross the input catcher cavity gap from negative peak to positive peak of the gap voltage. They only participate. Others do not participate. Therefore, at the output cavity gap, there exists bunches. In between bunches, there exists certain unbunched electrons also. Therefore, this state of affairs can be described as an AC, a periodic AC, and it can be expressed in Fourier series as I2 T2 equal to I naught average plus N1 n equal to 1 to infinity 2 I naught Jn. J stands for Bessel functions. N is order. N x. X is bunching parameter. Cos n omega t2 minus theta naught minus theta g. Theta naught is transit angle pertaining to drift space. Theta g is transit angle pertaining to grid gap. Here Jn's represent Bessel functions of first kind. Notice the current has infinite number of components, and out of this only primary or fundamental component is useful to amplify the signal. Its amplitude is 2 I naught J1x. Okay, this is the amplitude and fundamental component. Fundamental component means n equal to 1. So this is the amplitude. This component assumes maximum value when J1 is maximum. I2 is maximum when J1 is maximum. Maximum value of J1 is 0.58 and it assumes this value when its argument bunching parameter is 1.841. This piece of information is useful while calculating maximum possible efficiency or maximum possible output power from the device. Now, output power. An expression for the output power of Klystron can be obtained from its equivalent circuit as P out is beta naught I2 whole square by 2 or shunt RSH. Here beta naught is beam coupling quotient of the output cavity. I2 is amplitude of the fundamental component of catcher cavity current. This 2 has come into being because power is proportional to RMS current square. Amplitudes can be converted into RMS values by dividing with root 2. Now one can understand why 2 is present in the expression RSH. What is RH? SH. RSH is equivalent resistance of output cavity. It is equal to parallel combination of 3 resistors. Wall resistance RSHO, beam loading resistance RB, and external load resistance RL. The amplitude of fundamental component of induced current in the catcher cavity is, this is induced current. Notice in the earlier slide is shown an expression for I2. Induced current is beam coupling quotient multiplied by the current in the beam. Therefore, I2 induced is beta naught 2 I naught J1 x. Thus, the power output becomes P out is beta naught I2 whole square by 2 RSH, which is equal to beta naught I2 V2 by 2, which is equal to beta naught 2 I naught J1 x whole square by 2 multiplied by RSH. Now we consider another parameter, electronic efficiency. The electronic efficiency by definition is the efficiency with which electrons transfer energy from DC voltage source to AC voltage signal. Mathematically, it can be written as eta is equal to P out by P in. Efficiency is always output by input. P out by P in. In case of two cavity klystron, the beam takes power from DC source and it is equal to I naught V naught. This is accelerating voltage. This is current and delivers an amount of AC power to signal equal to beta naught I2 V2 by 2. Thus, electronic efficiency of the device becomes, the P in is I naught V naught. P out is this one. The ratio gives efficiency. Some more points regarding electronic efficiency. The efficiency assumes maximum value when all its factors assume their respective maximum values. Coupling quotient assumes a maximum value of 1 when the coupling is perfect. It is an ideal. In practice, it's always less than 1. It may be 0.9 or it may be 0.99, but it cannot be 1. The maximum output current I2 equal to 2I naught J1X is 2I naught into 0.58 because maximum value of J1 is 0.58 and maximum theoretical possible value of output voltage V2 is V naught. V2 cannot be more than V naught. Thus, maximum theoretically possible electronic efficiency, it becomes 58%. In practice, it is not even 58. 58 is small because efficiency 58% means 42% of the input is getting wasted. This is one aspect. Another aspect is this is theoretically possible, maximum efficiency. But in practice, it is not so. It cannot be even 50%. Reason is only half of the beam, electron beam, is participating in the amplification process. So half of the energy input to the beam, it is going waste. Therefore, efficiency cannot be 50%, even 50%. The efficiency is dependent upon catcher cavity transit angle. It depends upon so many parameters. It also depends upon catcher gap transit angle, theta g. When angle is small, efficiency is large. So gap should be small. Theoretical maximum value is 58%. In practice, however, it is always in between 15 to 30%. Notice there is a saying, a statement of fact. With increase in frequency, the cost of generating a wave, it increases tremendously. It means power at microwave frequencies is quite expensive when compared to power or wave at frequencies falling in kilohertz or megahertz range. The reason for this expensiveness lies in the fact that the devices that generate, that produce the high frequency power, high frequency wave, they are highly inefficient. In practice, it is between 15 to 30%. Okay, we can consider 25 as efficiency. Even in this case, what is happening? 75% of input is getting wasted. Only 25% of the input is getting converted into useful form. These are some of the things I want to share regarding the parameters that describe the operation of Klystron amplifiers. To recap, average gap voltage, beam coupling quotient, equation of velocity modulation, bunching parameters, output power, electronic efficiency, and some other parameters are also introduced, described, and explained in the present session. Hope you have a fruitful and successful and enriching and transformative learning experience. Enough for now. See you again soon in another session. Bye bye.